Hello, welcome to this lecture on biomathematics. In the last lecture, we have been discussing Fourier series and how to find Fourier series for some particular functions, where we said that any periodic function can be represented as sum of sines and cosines. And today, we are going to discuss something related to that, but little more generalization of this, where our today's topic is called Fourier transforms. So, the topic is Fourier transform, and this is Fourier transform is essentially it is related to Fourier series, but it is much generalized version of this, little more it is more general, and then it is not for periodic function alone, it is more general, and this has much wider application in some sense, and this can be also done for continuous cases, where in the previous cases we used to write sums, and here we will write only mostly integrals. We can also write sums here too, but today we will discuss some integrals, the way continuous the way we have written. We will come and see, we will see this in a minute, but the topic of today is Fourier transform. Now, why Fourier transform, what is Fourier transform, etc., we will come and we will see this. But to say, let us take this particular example of a sine wave or a cosine wave. So, to specify a simple sine or cosine wave, one has to either draw it in paper, that is draw it in space, or just specify its frequency. Both of, if I want to tell you that like sin x or sin 2x, sin 3x, what do? I just draw this. So, sin 0 is 0. So, I draw like this. So, this is pi by 2, this is pi, and this is 2, this is 2 pi. So, similarly, so this is basically sin x. So, now because it reaches from 0 to it completes a cycle in 2 pi when x is equal to 2 pi. So, this is x and this is sin x. When x is equal to 2 pi, it forms a complete cycle. So, this is essentially sin x. Now, either you can draw this, or you just say somebody that is a sine wave with frequency 1. So, what is frequency? So, we can define, so you can define in general sin k x. So, here k is 1. So, here k is 1, because this is just sin x. So, you can just specify k, because if you specify k, you can have a different, if your k is 1, you have sin x, if your k is 2, something else, k is 3.5, some other kind of a wave. So, just by specifying either I can say it is a sine wave and with k 1 or k 2, everybody will understand immediately the shape of it. Or you can just show this shape and then show this, either you can show this shape, then people will understand that this is sin x, or you can say that it is a sine wave with, it is a wave with k, it is a sine wave with k equal to 1, then also people will understand this. So, there are two ways of telling people, either you can just show the function by plotting it, or you can just say that it is sine wave with k equal to sin k x with k equal to 1, then we will easily understand this. So, look at here, what we have plotted is the red color is sin x. So, in the blue color it is sin 2 x. So, here k is 1, here k is 2. So, if we are talking about sine wave and we say that sine wave with k equal to 1, people will immediately understand this red curve, or we can say sine wave with k equal to 2, then they will understand that it should look like this blue, or you can plot this and see. Then also people will understand that this is actually sin x or sin 2 x. So, there are two ways of representing it. One, you can represent it as you can specify the function as a function of x, or you can specify something as a function of frequency, which is k. So, what is k? K is essentially this frequency here. So, we define this k as spatial frequency. So, if we have sin kx or cos kx or even e power I kx, which is a combination of sin kx and cos kx, you can call k as spatial frequency. You can do exactly same thing with time. You can either say sin omega t, cos omega t, e power I omega t, where omega is also frequency, it's temporal frequency you could say. So, both whatever we said so far either apply for k or omega. So, there is either space or time and there is corresponding frequencies. So, now what is the deal? If you have this, how is it related to Fourier transform? Okay. Mathematically, if you imagine a function and this represents the wave in space. So, you can have sin x, cos x. So, f of x is a function which represents the wave in space. In space means in paper. In paper is 2D space. So, any some f of x, you can imagine an f of x which is representing a wave. So, f of x could be sin kx, f of x could be cos kx, f of x could be e power I kx. So, this is the most general f of x which is representing a wave, because this is a combination of sin and cos. So, given that you have a combination of sin and cos, which is e power I kx, then this represents a wave. So, that is the function which represents a wave in space. So, if you plot it, you will get a wave. Now, you can also imagine a different function which represents the wave given its frequency. So, given k, you can represent a function and say, you can say that this will be a wave with this particular frequency. So, now the relation between this f and g, the way we transform a function in real space or in paper to an equivalent function in frequency domain is known as Fourier transform. So, the relation between f of x and g of k is typically called a Fourier transform. So, we will see what exactly this relation is, but one can imagine a relation between f of x and g of k, and this relation is called Fourier transform. So, now what is the relation between f of x and g of k? The relation between f of x and g of k is the following. If you know f of x, you can calculate g of k in the following manner. You multiply with e power minus 2 pi I kx and integrate with x, integrate over x. So, this is the definition of g of k. So, you integrate over x, then the answer will be a function of k only. So, for a given value of k, there is a g of k, and for a given value of k, you can find out many values of for different values of x, you have e power I 2 pi kx, and then you multiply with the f of x and integrate it, you get g of k. Note that this is from minus infinity to infinity. So, yesterday when we were discussing, we defined something called Cn, which was minus pi to plus pi f of x e power I n x. Here today g of k, which is minus infinity to infinity f of x e power I 2 pi k x. Small difference, like this essentially you can write this, you can also write if you want g of k as 1 over 2 pi into minus infinity to infinity f of x e power I k x dx. This is also a definition. So, one can define C of n this particular way. There is a 1 over pi here yesterday also. So, there is a relation, we can see that there is a generalization of this. There is an f of x, but the limit has gone from minus pi to plus pi to it was minus pi to plus pi yesterday. Here it is minus infinity to infinity in the Fourier transformation. So, you can understand this, and this is the definition of g of k. Okay. So, now you have g of k. So, what does this all mean? We can define some g of k. What does that all mean? Now, let us say that I want to say that there is a wave, sine wave or cosine wave with frequency 2. What does that mean? So, let us for simplicity, let us do this thing called E. So, before just going to an example, just what we saw here is that if you know f of x, you can calculate g of k through this particular relation, and if you know g of k, you can calculate f of x by inverting this, and this is called inverse Fourier transform. That is how to calculate f of x given g of k. So, it is exactly same thing, but this minus becomes plus here. It was f of x e power minus 2 pi I k x. Here it is f of x. Sorry, here it is g of k e power 2 pi I k dk. So, this is a plus sign here. So, there is a difference here, and integral over k will give you f of x. So, this is the way of knowing f of x. This is the way of finding g of k, and if you know g of k, you can also find f of x in this particular manner. So, this is the complete Fourier transformation and inverse Fourier transformation. Fourier transform and inverse Fourier transform. Okay, so you know Fourier transform and inverse Fourier transform, and let us do an example. Let us now think of a little more carefully about this. Now, we can take, let us say we have f of x. What did we see? We just saw that integral minus infinity to infinity f of x e power I k x dx is what we call g of k with a 1 over 2 pi. I can define also this way, or I can define 2 pi, write 2 pi here also. There are two ways of defining, as I said. So, I will sometime use this definition. Okay. So, now let us say that there is a f of x that we know. So, we want to consider a wave, f of x is a wave. So, let us say I want to represent like a wave sine 3x or cos 3x. So, the general form of sine 3x or cos 3x is like e power I 3x, which is essentially cos 3x plus I sine 3x. So, this is the most general form of a wave with frequency 3. So, you can say that either cos 3x plus I sine 3x, or you can say that a wave with frequency 3. So, you have those two ways of saying. Either I can say cos 3x plus I sine 3x, or I can say a wave with frequency 3. So, this is e power I 3x, and this I will call f of x. Now, I want to go and find out this function, which is my g of k, which is here k is 3. So, essentially I will get essentially g of 3. So, I want to find out how do we say this mathematically. So, to find out what is the way of saying this mathematically, that is, it is a way with the frequency 3, the way to do is to do Fourier transform of this. So, let us do this. Fourier transform of integral minus infinity to infinity f of x e power I k x dx with 1 over 2 pi. This is equal to 1 over 2 pi minus infinity to infinity. F of x can be written is e power I 3 x e power I k x dx. Now, e power 3 x into e power I k x can be written as, sorry, there is a minus sign. This was, I am just going to use this definition with a minus sign, because that is what we discussed. So, this is my g of k. So, this is my g of k. So, now how do I get g of k? So, how do you do this integral? What is this integral? So, I can write this as integral minus infinity to infinity. There is a g of k is equal to e power I 3 x minus e power I k x. So, e power a minus into e power minus b is e power a minus b. So, this can be written as e power I x into 3 minus k into dx. So, 3 minus k can be, this can be written this particular way. So, it turns out that yesterday we were saying, so the answer to this is something called Dirac delta function that we discussed yesterday briefly. I will tell you a little more about what is the Dirac delta function. The answer of this is delta of 3 minus k. What does that mean? So, this delta is called a Dirac delta function. Dirac delta function, this was named after a famous scientist called Paul Dirac. So, now what does this mean? What does this delta of 3 minus k, what does that mean? It means that this function has a value only when k equal to 3. Whatever inside this bracket has to be equal. The total of this should be 0. So, when k equal to 3, this will become, whatever inside this bracket will become 0. So, when k equal to 3, this has a value, everywhere else this has no value. So, if I plot e power I 3 x cos 3 x sin k x real, so like you might get some function like this. Now, this is my f of x versus x. Now, if I plot my g of k versus k, so this is my f of x, which is cos k x plus I sin k x. So, I can plot actually real part and imaginary part separately, but essentially it will look like a wave, and the Fourier transform of that is just one line. This point is k equal to 3. So, only at k equal to 3. So, this is f of x and this is g of k, which is delta of k minus 3 or 3 minus k, they are equal. So, delta of k minus 3, that is only when k equal to 3 you have this value, everywhere else. So, it was written delta of 3 minus k, so let me write the same thing, delta of 3 minus k. So, only when k equal to 3 you have a value, nowhere else you have this value, everywhere else the function is 0. So, this is representing the function in real space, and this is representing the function in the Fourier space. So, mathematically, if you know about Fourier transforms, one can either draw this function law like this, or you can just draw a line like this. Both represents the same thing, same information. So, this is giving you an information delta of 3 minus k is the information is saying that it is a wave with only frequency value 3, only frequency value 3. So, that means only here. So, you can represent either like this or either like this. So, this is the relation between this two, g of k and f of x. The way of finding this, known this you can find this, and known this you can find this. This is called Fourier transform. So, this is called Fourier transform. So, what we just discussed is something called Dirac delta function. So, you can also define it as e power 2 pi I k x dx. So, you can define it as delta of k, and if do 2 pi I k minus b into x dx is called delta of k minus b. So, we had b equal to 3, that is because we have e power I k minus 3b 3x. So, essentially k minus 3x. So, essentially we had delta of k minus 3 in this. So, this is, if you plot delta of k minus b, so this is k equal to b and this function is delta of k minus b. Only value, the function has only value at k equal to b, everywhere else the function is 0. Such function is called Dirac delta function, just value only at one point. Okay. So, now what are we, why should we learn Fourier transform at all? Why Fourier transform? It turns out that why we should learn Fourier, one reason is this. So, it turns out that in many scattering and diffraction experiments, the output one gets is g of k. So, we just discussed g of k, which is a function in the k domain, in the frequency domain. So, for example, if you do X-ray scattering experiments to find out the crystal structure of a protein, typically what you would get is some answer in the k domain. So, if you can ask people who do X-ray scattering or people familiar with X-ray crystallography, you will see that they will tell you that what they will get essentially is something in k space or g of k, some value, some function in the k space. So, this is also true for other experiments. Any scattering experiments you do, let us say you want to find out the proteins, then people find something called structure factor and various other things in when you do scattering experiments to find polymer information about the structure of polymers or any structure for that matter. When people do scattering experiments, what they get essentially as an output is something called structure factor, which is essentially g of k, the function in the Fourier space. So, if you know g of k, you have to really find out, if you get g of k, if you really want to find out the structure of the protein, which is f of x, you have to do this inverse Fourier transform. So, you have to know the Fourier transform essentially to get the real curve in 3D space. If you know some cryptic information like information in the Fourier space, it's like you know some cryptic information and then you can convert into real space information. Like if somebody tells you, if you don't know Fourier series and if somebody tells you, okay, what you get is this with k equal to 2, you need some expertise to convert. Actually, okay, this means it is a wave like this. So, you need some expertise to know that this is essentially what if you get the output g of k as this, the wave has to be like this. You can sometimes get g of k as like this, then the wave has to have some particular form. So, all this information, how if you know g of k in a particular manner, if you get two peaks, let us say you get like one here, one here. So, let us say this is k equal to 1 and this k equal to 5. you get two peaks. What does that mean in the wave space? So, what are we getting here? We are essentially getting delta of k minus 1 and delta of k minus 5. When k equal to 5 you have a value and k equal to 1 you have a value. So, this is the two functions, and so this is your g of k, and then you have to ask how does actually the wave look like. So, to find such answers, to answer this, one has to know how do we do the Fourier transform of this to get this. So, Fourier transform of delta of k minus 1 if you do. So, you can do delta of k minus 1 into integral dk e power I k x dk will give you essentially e power I, only when k equal to 1 you have value. So, you get e power I x. Similarly, only when k equal to 1 you have value. So, you get e power I x. Similarly, when it is delta of k minus 5 e power I k x dx, what does that mean? This means that only when k equal to 5 you have this function. So, this answer of this is e power I 5 x. So, if you have such two peaks, the answer f of x is essentially e power I x plus e power I 5 x. This is essentially cos x plus cos 5 x plus I sin x plus I sin 5 x. So, this is essentially the real function, and this is the function in the Fourier space. So, knowing this, how can we convert to this? That is what essentially Fourier transform tells you. Okay. Given some peaks, from that you have to convert to some real functions which has some meaning which you can think of. Okay. So, now how do we know this delta of k minus 5 e power I k x is e power I 5 k 5 x? So, the definition of Dirac delta function, when you define, there is one definition is f of x delta of k minus a dk is essentially f of, sorry, I wrongly wrote this. So, integral f of x delta of x minus a dx is essentially f of a, or also you can write integral f of x was e power I x, sorry, f of x was, so if we have this f of x was e power I k x, and there is delta of k minus 5 and you have dk, then this is essentially e power I 5 x. Instead of k I should substitute 5, and this is the answer. So, this is essentially the definition, or if you want to write g of k delta of k minus b dk is essentially g of b. So, this is the definition of the delta function, Dirac delta function, which means that this is 0 everywhere all except at k equal to b, everywhere else this is 0. So, delta of k minus b equal to 0 if k not equal to b, delta of k minus b is actually infinity at k equal to b. It has a value at k equal to b. Okay. So, this is the Dirac delta function that we have. So, now there is, so one use of this is that, so what when you do X-ray crystallography or such scattering experiments, what you will essentially get is g of k, and then you have to get some idea about sin x, how the curve look like. Okay, now one can use also Fourier transform. You can also use Fourier transform and other similar transform to solve differential equations. So, if you have a differential equation and if you most of the time if you do Fourier transform, it becomes easier to handle this this differential equation and solve it. So, we will see some examples of this in the coming lectures. How can we solve Fourier transform or similar use some Fourier transform or similar transforms to actually study and understand some differential equations. So, we will come to that. So, now we will look carefully, little more carefully into the transformation we were discussing. So, we were discussing essentially we were discussing that if you know f of x and if you have e power I k x and dx integral minus infinity to infinity 1 over 2 pi, and we call this g of k. Now, one can write e power I k x as cos k x plus sin k x. So, this is minus infinity to infinity f of x into cos k x plus I sin k x. So, this is 1 by 2 pi. So, this is also g of k, because e power I x can be written as cos k x plus I sin k x. If you know cos k x plus I sin k x, we can rewrite this essentially this cos k x plus I sin k x as 1 by 2 pi minus infinity to infinity f of x cos k x 1 integral plus I into 1 by 2 pi into minus infinity to infinity f of x sin k x dx. So, essentially this can be written as a cos integral and a sin integral. So, Fourier transform is essentially like a cos integral and a sin integral. So, this is essentially our g of k. Whatever this gives you g of k. Now, so this kind of a form is called a trigonometric form, if you like. That is, given this function f of x, you can write this in the form of sines and cosines. So, this is called a trigonometric function. So, this in the trigonometric form, if you use the other, if you use e power minus 2 pi I k x, you can write it as 2 pi cos 2 pi k x plus I sin minus I sin 2 pi k x, and g of k in that case, if this is the definition you are following for Fourier transform, like f of x cos 2 pi k x minus I sin 2 pi k x. So, you can write f of x cos 2 pi k x dx minus I sin 2 pi k x dx. So, essentially you get this relation between f of x and g of k. So, what does that mean? What is the advantage of having this? So, let us say that you have f of x which is, let us say, an odd function. So, what does that mean? F of x is equal to minus f of minus x. For example, if f of x is just x, this is an odd function. What does that mean? When you put a minus sign, is just minus of f of x. So, if you go to the negative part, this is just a minus sign. For when x is negative, the function is minus sign of the positive part. So, the negative of this is this, negative of this is this, negative of this is this. So, this is an odd function, and in such cases, when it is an odd function, you have to just only the sign part remains, the cos part goes to 0. So, for an odd function, the g of k can be written as 0 to infinity f of x sin 2 pi k x. This is a simple property of sine function. You can just check what is the property, because what happens is that we just saw here that we can write this as f of x sin k x and f of x cos k x. Now, you can use the property that it is an odd function, and you will end up that you can rewrite this particular way, and if it is an even function, you have to just do this cos integral. Why is this? So, we will come and see why, but this is, you can take it as an exercise and just put f of x as an odd function. You can use the original definition and take f of x as an odd function or an even function, and then try using what you get. So, you will find that one part goes to 0, and what essentially you have is this. So, for an odd function, even function, the definition becomes just this. Okay. So, now we have this simple, we can simplify this particular way. Okay. So, what did we essentially, the message is that if you know a function f of x, you can do a Fourier transform and get a function which is a function of k. And we saw that if it is a wave, then the Fourier transform of that is just a peak, just a line like a delta function. So, every function has its Fourier transform. So, it turns out that if the function is a Gaussian, if the function is just a Gaussian function, so let us say f of x is e power minus a x square, its Fourier transform g of k turns out to be e power some other b k square. It has the same form, same functional form. This is also a Gaussian. So, the Fourier transform for a Gaussian, so this is it turns out that it is just this itself. So, how do we will try and do this later in another lecture. We will try and prove that this is indeed this, but you can try doing this, but you can show that this is indeed the Fourier transform. Or if you know the f of x as e power minus a x square, the g of k turns out to be this. If you have something called Lorentzian, which is 1 over x square plus a square, let us say this is your f of x, then what is g of k? It is essentially minus infinity to infinity e power I k x into 1 over x square plus a square dx. And if you do this, the answer you get turns out to be, I think, e power minus k into a. So, you will, if you do this, you will get g of k, which is essentially e power minus k. So, this is your f of x. So, this is, so we will see how one gets all this f of x and g of k, but what I am trying to say here is that for every f of x, there is a g of k. One can calculate a g of k. So, this way of calculating, this is Fourier transform. So, you do a Fourier transform to get this, you get an inverse Fourier transform to go back. So, this has enormous use in different fields, like especially like in biomedical engineering and many such fields, like the enormous usage where signals, many things that is a function of time, many signals that is as a function of time which you get, like some signals that you will be getting as a function of time, which is some function of t, will be can be converted to some function of the frequency omega, which is defined as integral minus infinity to infinity f of t e power minus I omega t dt. So, in this particular way you can convert, there is a 1 over 2 pi. So, this is some ways you can convert the information in the t real space to a frequency space information. So, this is essentially converting information from one language to a different kind of a function, and this has enormous use. We will discuss the use of this in the coming lectures, but at this moment it is suffice to say that Fourier transform is a very powerful technique. This can be used in many different ways, and it can be written as a sine transform or a cosine transform in some sense, if it is an odd function or even function depending on that. So, it has its own in scattering and X-ray crystallography, it has wide range of uses, especially in all sorts of optics, essentially all optical experiments, even including like let us say you have spectroscopy. In spectroscopy, Fourier transform is extensively used. So, to understand the principle behind all this, one should clearly learn the basics how to do the Fourier transform. So, that is the important point which we should learn. So, we will have some exercises related to this specified how to do. We will also in the coming lectures we will discuss how do we actually do Fourier transform of various functions, and we will also see how do we use this Fourier transform actually to solve differential equations. We will take some differential equations and solve them using Fourier transform or similar transformation. So, I will briefly tell you one another transformation which is very close to Fourier transformation. So, this integral minus infinity to infinity f of x e power I k x can be also written as a sum of n is equal to, let us say, minus infinity to infinity some f of x, f of n e power I n x dx. So, this way also no need of dx because we are converting this to a sum. So, f of n e power I n x. So, you can convert this in a way to a discrete form also. So, there is an equivalent transform one can actually write in a discrete way some other transformation, let us say sum over n some function f n z power n. So, such thing can be written as some g of z. So, this kind of a transformation is also a generalized form of Fourier transform. This is called Z transform minus infinity to infinity. So, you can also write this in a different way, same like you can if you can also write, let us say we can write this f of n e power minus z n sum over n is equal to minus infinity to infinity and you can write g of z. So, this z, you can also write e power minus z n. So, there are different ways of writing this. So, such transformation, this sometimes called z transformation, but they are all essentially some kind of a generalized version of Fourier transform. So, we will discuss all this when we need it. We might be able to use all these transforms to do some simple studies on various differential equations. So, to summarize, essentially what you have to look is just this slide. Here you have Fourier transform and inverse Fourier transform. You have a function f of x, and that can be converted to a function of k, g of k in this particular fashion, and that can be inverted to get f of x back. So, if you know f of x, you can get g of k. If you know g of k, you can get f of x in this particular fashion. So, this is the essential summary of Fourier transform, and this has a lot of usage in different fields. So, there are different, just one more thing I should say, like some places there are different ways of writing this, as we just saw. Sometime you will write, you will see this written as g of k as 1 over 2 pi integral f of x e power I k x dx. Some of them it will be, some of the time it will be written 1 over 2 pi. So, some of the time you will see this written minus infinity to infinity, all of this is minus infinity to infinity, f of x e power I k x dx. Sometime you will see g of k as just minus infinity to infinity f of x e power I 2 pi k x dx. So, this some people write 1 over 2 pi, some over 1 over root 2 pi. So, correspondingly all of these definitions are correct and they are essentially the same, but the only thing is that for each of them the inverse transform is slightly different. So, that means this has, when you define inverse Fourier transform, you do not have a 2 pi. Here both in transform and inverse Fourier transform you will have 1 over root 2 pi, and here both inverse Fourier transform will have this 2 pi here, transform and inverse Fourier transform. So, you can just stick to one of this definition and follow this. You can, if you look at textbooks, you can see, you may see any three of this, any one of this three. You might see sometimes this, sometimes this, sometimes this, but follow the same definition and its inverse definition. So, here the definition which I use here in the slides is essentially f of x e power minus 2 pi I k x and its inverse is g of k e power 2 pi I k x. So, this is a pair and this pair is complete. Similarly, if you write 1 over root 2 pi, the inverse will have also 1 over root 2 pi here. So, depending on each of this, the inverse is slightly different. Look at the textbooks, whichever textbooks. This is just a warning for you, because when you look at the textbooks, you might see any of this and you shouldn't get confused. Just remember that any definition will have its inverse correspondingly. So, just follow the same rule, same definition for Fourier transform and its inverse definition from the same book. Be consistent with that. That is all it is. Okay, so, this is essentially the summary. To summarize, you can define a Fourier transform and inverse Fourier transform and convert functions from real space to frequency space, or what sometimes people call it k space, sometimes people call it omega space, frequency space, q space. So, you can convert a function from a real space to a frequency space, and that has a lot of use in different fields, and we are just trying to understand the beginning of this, so that it might be useful for biologists, especially in the context of X-ray crystallography, in the context of differential equations, in the context of biomedical engineering, and so on and so forth. Okay, so with this we will stop today's lecture. Bye.